Hi everyone, I'm Lynn Trong with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Andrew Poerschke and Robert Beach with IBACOS here today to discuss high-performance HVAC, low-load and plug-and-play HVAC systems. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You can either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, you'll eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will show the telephone number and audio pin for you to use to dial in. Panelists, we ask that you please mute your audio device while you are not presenting. If you are having difficulties with the webinar, you can contact the GoToWebinar's help desk for assistance. If you have a question during today's webinar, please use the questions pane to type in your question. Also, we're recording the webinar and we'll have posting PDF copies of the presentation on the Building America website. If you, in a few weeks, we'll have the recording available on DOE's YouTube channel, and we'll also be posting that on the Building America website as well. Before our speakers begin, I'll provide a short overview of the Building America program. Following the presentations, we'll have a question and answer session and closing remarks. For more than 20 years, the U.S. Department of Energy Building America program has been partnering with industry to bring cutting-edge innovations and resources to market. This Building America webinar presents an overview of IBACOS's project, HVAC project. And for now, for today's presentation, our webinar today is Building America, Low-Load and Plug-and-Play HVAC Systems. Our speakers today are Andrew and Robert with IBACOS. Rob has over 16 years of modeling, prototyping, and design experience. He has contributed to numerous space conditioning, enclosure design, and market analysis projects with a specific focus on modeling, graphics, and data analytics. Andrew conducts research on building performance and has advanced energy modeling and computational analysis experience. He has conducted research on innovative space conditioning technologies for the past 5 years. With that, I'd like to hand it over to our first speaker today, which is Andrew Poerschke with IBACOS. Andrew?
All right, thank you. So I'm Andrew Poerschke. I am a specialist within the innovation programs at IBACOS.
And my name is Robert Beach. I'm also with IBACOS as a specialist in the innovation programs as well.
Yeah, and so thank you for your time and attendance today. We will be going over the plug-and-play duct research that IBACOS has done. This work is the culmination of about 1.5 years worth of work that IBACOS has been doing as part of the Building America program funded by Building America. So a brief agenda. Today we're going to go over some of the background with HVAC, some of the reasons kind of why we're talking about this today, and then we'll go into the plug-and-play concept in some detail, and then we'll go through the Building America project and the specific things that were learned through the course of that project, and wrap up with some conclusions. And then there'll be that time for question and answers at the end. So why ducts? It's 2017. Why are we talking about duct systems? We have an image here from a 1941 homeowners magazine showing a possible duct system for a brand new production home that's almost 75 years old. So looking at this image, we see a duct system that's very similar to what is being installed, designed, and installed in homes today. So in 75 years, very little has changed in residential HVAC duct systems. And so we think there's a huge opportunity here for some innovations in this industry, in the field, that can really help with performance and installation in various aspects. And so we think the time is ripe to be reconsidering ducts and duct technology and ways to really bring that kind of into the modern era. So some general trends in HVAC. First of all, what's really driving things is the fact that buildings are changing. You know, in the last 10 years or so, there's been a large uptick in nationwide code adoption for more and more efficient codes and standards. So homes are becoming more and more efficient. Along with that, you know, homes are also becoming larger. So we have, you know, these shrinking loads, these shrinking airflows from HVAC systems, but still very large homes to maintain comfort in. And so there's this shift in the way that HVAC systems and duct systems have to work in order to provide comfort. There's also this interest and desire in bringing ductwork into conditioned space to help improve the efficiency and comfort of homes, and that can be difficult with conventionally, you know, large-sized ductwork on the large trunk and branch layouts. There's also then a challenge in maintaining velocity and mixing across a range of system operations as we start to introduce variable capacity systems, that there's, again, greater risks that there might be comfort issues within a home. There's also trends and challenges within the industry itself. Currently, HVAC systems are complicated to design and install. And along with that, there's challenges in finding skilled labor. There's certainly a labor shortage right now, and especially when it comes to skilled tradesmen who are able to install well-performing HVAC systems. So we see that as a challenge to kind of overcome with new technologies. And then also there's often a complicated or time-consuming commissioning and rating processes, which are another challenge to overcome. So IBACOS has been working in the construction industry for the last 25 years. IBACOS has been working with home builders, with trades, product manufacturers, all aspects of the industry, you know, looking at ways to make better homes. With that, IBACOS has really been focused on HVAC and ways in which, you know, HVAC systems, air distribution systems can be best optimized to provide comfort and ideal performance and efficiency within homes. And so some of the things that IBACOS has looked at that kind of have brought us to the technology and innovation that we're looking at today, kind of the path that we've gone along is looking at ways to simplify the air distribution system by reducing duct lengths, reducing the duct complexity. We've considered various scenarios and have done testing in various lab houses throughout the years. One thing that IBACOS has considered is, you know, taking it to the extreme of a single point of air delivery for an entire house and trying to rely on passive methods to mix air between the rooms. You know, at that end of the extreme, you know, we weren't able to provide comfort. And, you know, basically the conclusion of a lot of this work is that we really need to provide some level of conditioned air into each room, into each zone of the house in order to provide comfort. And so, you know, that's one of the primary important things. And then also throw and mixing is an area that IBACOS has done research in to understand, again, once you get air into a zone, how does that air interact with that space? And you know, we've done work looking at high sidewall registers and how those can provide great comfort within a home. So now we'll talk about this plug-and-play duct concept. In many ways, this is really the culmination of many years of research into trying to understand what the ideal duct system might be, both from a comfort, performance, and efficiency standpoint, but also from an installability and a kind of a consistent quality product standpoint. So the concept here again was really to simplify the design and installation process of ductwork. We were primarily, you know, looking at ways to ease various pain points within the industry, and that's what's brought us to this plug-and-play duct system. So at its most basic level, this is a home-run duct system. It's very akin to PEX in that you have, you know, home-run duct runouts connected to a central manifold. Along with that is a simplified design process that we've been developing. The way this system works, the way that we're envisioning it, is that it's a single duct size and a single fitting size, and those ducts are selected in order to deliver the amount of airflow needed to a room. So one room might get 2 ducts, another room might get a single duct. And this is somewhat different from conventional systems where the diameter of the duct is sized. So you might have a 5-inch or a 7-inch duct today. With the technology that we're proposing, you would have maybe 2 ducts or 3 ducts even to a room. All of this, we believe, would simplify, greatly simplify the installation process. So to go into a little more detail here, we're talking about smaller diameter ducts. We've looked at ducts somewhere between 2 and 3 inches. We think that there's a sweet spot, somewhere between maybe 2.5 inches and 3 inches. And the idea is that these ducts are small enough that they can be easily installed within interior walls and within various interior cavities, so that it's very easy to put the ductwork completely within conditioned space. A lot of the work that we've done has focused on semi-rigid materials. So this is basically PVC pipe, and it's a very easy material to work with. It has a smooth inner wall. It's a material a lot of the trades are already familiar with, and so it's what we based a lot of our work on. There's also the idea of a central accessible air distribution manifold that all of these ducts connect to. And we think that this technology really has the promise to have a leak-free duct installation without the need for extra sealing and extra time-consuming steps to ensure that there are no leaks. So plastic was the primary material that we considered in this work. As we go through this presentation, you'll see that we also looked at some other materials. One of the primary issues with using plastic as a duct material is that it doesn't meet the UL 181 standards for flame and smoke spread as an air delivery conduit. And we'll get into some more of that, but we also considered some flexible duct materials that would pass the UL codes. So what's the opportunity here? We've drawn the parallel to PEX plumbing, and PEX plumbing really shows is a great case study for how a new technology that streamlines the design and installation process can really take over a large market share quite rapidly. PEX saw a huge explosion in adoption over the course of literally a couple decades. A large part of that was also rising cost of copper and other trade issues, but we think that the plug-and-play system is poised to revolutionize ductwork in a similar way that the PEX and the PEX home run manifold system really revolutionized plumbing. And just as another kind of point of perspective, we think that the residential ductwork industry is a very, very huge industry. We're talking about roughly $1 billion annually in the U.S. So we think it's really a ripe opportunity for some large-scale innovations in this area.
So hi, this is Rob Beach speaking now. I'll just quickly introduce the next section, which is going to go into detail about the Building America project itself. For the project, it's really the primary focus of this webinar. For the Building America project, we're looking at early testing and validation of the plug-and-play concept, and we went through 5 key areas. The 2 main areas being performance in the home in terms of temperature distribution, as well as cost. So we looked in detail at those 2 areas. We also had facets of the project related to engaging with the industry, digging in a little deeper with regards to some of the code issues that we see with plastic ductwork, and demonstrate the system in comparison to some systems that are currently out there, such as trunk and branch systems. So the next sections we'll go over first the design methodology and kind of our thinking behind the development of that simplified design method. We'll go through some component testing that we did, which was looking at sort of gut check data to be able to feed into our simulations and into the design tool, and to understand the different products, duct products, in relation to one another. We looked at the lab house testing, where we installed a complete system in a lab home to kind of, again, get some data to validate our simulations, to understand how the system is performing as installed. We conducted primarily a series of simulations to be able to compare many different configurations of the system in multiple climate zones and under a variety of homes. And then lastly, we'll go over the cost discussion. We did a series of time and motion studies as well as cost estimates for installed systems to be able to compare and evaluate the cost of what this cost might be. And we'll wrap up again with some conclusions that were born out of this work.
Okay, and this is Andrew again, and I just wanted to bring up the point that, this presentation here is a relatively condensed version of our overall effort. There will be a detailed report eventually published by the DOE on the work that we're doing. So just keep that in mind, that this is really just, we're trying to give you the tip of the iceberg on many different areas, but there's a lot more depth that will be available. So to start talking about the design method here, we needed to understand some major parameters of this duct system. And our goal here was really to not reinvent the wheel. There's various standards out there for duct design, for overall HVAC, load calculation and design. And we wanted to base this effort off of kind of those existing bodies of knowledge. However, there were some, a few parameters that we really wanted to understand in greater detail. And those include the duct diameter, the duct material, the roughness and insulation, and how that can impact performance, the duct layout. So is this a compact layout system? Is it more of a sprawling system? And what impact does that have? And then also the design and installation process. We wanted that to be as streamlined and straightforward as possible. So again, the goal here with creating this design method for the home run plug-and-play system was to really be as simple as possible. We wanted basically the easiest approach that can still provide that expected level of comfort. And so as a starting point, we considered 4 different design methodologies. And through the course of the project, we really honed in on one, which we felt really provided that best balance of ease of use and accuracy and comfort. We kind of see a little cartoon rendering here of the 4 different design methodologies, basically from the most simple, where we assumed every duct got the same amount of airflow regardless of length, up through a scenario where we're considering the exact length of each run, the number of elbows, heat loss along the length of that duct. And ultimately, we settled on something of a middle road design methodology where the duct length and number of elbows is considered in predicting the airflow through the duct. But we erred on the side of not including thermal losses because it's very challenging in a streamlined tool to accurately predict that. And furthermore, because the ductwork is installed in conditioned space, any of those thermal losses would primarily end up in a zone within the house. And so it's another reason why it wasn't as critical to consider those losses. And then so ultimately, we needed to understand the pressure and flow relationship for different materials. And so we had done some testing to understand that. So to briefly kind of go through then this proposed design method, we've got some of the steps listed here. And so kind of at a basic level, this design method that we're proposing would start out with a standard load calculation. So you still have to know, how much energy is needed by each room to maintain comfort kind of at those peak load conditions. So you still have to do a manual J-type calculation. You would need to do a duct layout for the home run system to understand the rough lengths, the number of elbows, and those values are then used to understand the air that each duct is able to deliver. You would still need to perform a standard system selection, so your manual S, and out of that process you also are able to understand the amount of static pressure that's available to the system. And then where the new approach comes in is when it comes to the duct design. So that manual D, instead of needing to consider the trunk and branch conventional system with various fittings and duct sizes, this design approach instead, based on that available static pressure, is able to predict the amount of airflow that would go through each duct runout, and then select the number of ducts that are needed for a room. So if you have 2 ducts that each are delivering maybe 35 CFM going to a room, and that room needs 65 or 70 CFM, that room would get 2 ducts. Under the conventional mindset, that room might get, say, a 7-inch duct coming off of a main trunk. So that's kind of the major difference here with this approach compared to the conventional systems. And so this tool that we developed, we tested throughout this process. It shows a lot of promise, but we would certainly say that it's not quite ready for prime time. It still needs some vetting in the field. So it's definitely something of interest and something we're continuing to pursue, but not something that anybody should just pick up and try to employ on a day-to-day basis. So next we'll go over some of the detailed component testing that we did. We really targeted a few specific components to test in order to fill in some gaps in our knowledge. We primarily were looking at airflow through pipes and fittings, and so we'll go into some of those details. So, air movement through a duct is a very well understood phenomena. There's a whole established body of fluid mechanics that can describe air in all sorts of scenarios. And then there's also the HVAC industry and its established body of knowledge. And we wanted to really lean on that knowledge, but then also understand kind of in some very specific scenarios what kind of airflow we would get through various ducts and pipes. So we did kind of this limited set of tests in order to gain data to use in the design methodology, and this data was also then used in the set of detailed performance simulations that we'll get into later. So here's a quick snapshot of some of the materials that we tested. Again, in the report we'll go through in greater detail all of these, but we tested various sizes and shapes, very rigid ducts and also some flexible ducts for comparison. And then also we tested some different insulation values. Here's an image of our pressure testing setup that we used. This was based off of ASHRAE standard 120 for understanding the flow resistance of HVAC ducts. At a basic level, we had a fan which was measuring the airflow, and then using a manometer we were able to measure the static pressure loss along a test specimen. So some of the simple results here, as you would imagine, diameter is the biggest driving factor. And right here we have plotted the pressure drop per foot for various duct materials. And it's certainly a lot of data here. I don't expect you to process all of it. But you see that the 2.5-inch PVC pipe fits somewhere between the 2-inch PVC and this 3-inch flex duct. And these were the 3 materials that we primarily considered. 2-inch PVC is probably a bit too small for conventional homes, but we think, again, there's a lot of potential with something between that 2.5-inch PVC and that 3-inch flex duct. We also tested a number of elbows to understand their impact. And again, we needed this data for the simulations and the design methodology. we were able to convert things to effective length to use in the design methodology. You can see some of the data here. I'm not going to go into a lot of detail, but again, that will be available in the report.
So we conducted a very basic applicability study where we took some of this data and we also took the prototype design tool and we fed it through a scenario where we were applying designs to some floor plans of houses in multiple climate zones and also with multiple enclosures. We had very basic assumptions about what the duct system was and how it was laid out. And we were assuming pretty basic things like an available 0.35 inches of water of static pressure. And we just wanted a very simple check to see, what's the kind of limiting factor or what's the applicability that this system might have in homes across the U.S. So this chart here describes in binary form that simple analysis. And one of the conclusions from this is that this type of system is most appropriate for lower load homes, and that's always been our intent. And this chart really illustrates that. But it also shows that it's appropriate for homes that can be larger, particularly with different types of ducts and under different climate zones. So just as a gut check, we felt pretty good about how the system parameters were going to be able to apply to a lot of different homes across the entire U.S. among different enclosures.
Yeah, so then we saw that promise there from that applicability test, and we also then wanted to do some physical testing of this system in a real-world house. And so to do that, we installed a test system in our lab house, again, to kind of get that real-world experience of the installation process, of the airflow, and to do that in a case that wasn't occupied where we could be, severely influencing, somebody's comfort. We also used the data from this test house to compare with simulations that were based off of the house to make sure that we were capturing some of the dynamic behaviors that you see in the real world. So the lab house that we used is located near Pittsburgh, Pennsylvania. This lab house has been used for Building America research over the last 7+ years. And so we have a lot of kind of existing knowledge and experience with this house and the way it performs. And we've conditioned it with more conventional types of systems and more exotic types of systems. So we're able to kind of gauge the relative performance against that. This test house is very low load. It's near passive house levels of insulation and efficiency. We're talking about a total cooling load of about 1.5 tons. And so it's a highly, highly efficient house, and it provides us this test bed for easily installing different systems. One of the things that we learned pretty readily is some of the physical challenges and limitations with actually getting plastic ductwork within a ceiling cavity. So in the lab house, we installed the ductwork entirely within walls and within the ceiling cavity between the first and second floor. And we found ways around that, but it was certainly an interesting challenge to overcome. You'll see in the photos an example of some of the outlets that were used, and then also an example of a manifold located on top of a air handling unit. So the system that was installed, again, was PVC ducts. We had a total of 12 ducts for this house, and we were able to get by with 2-inch PVC pipe. Partly that was because, again, this house is such a low load that 2-inch ducts were able to satisfy those loads and that airflow. 2 inches probably isn't realistic for a more production scale type of house. So the house was tested primarily through the heating season using a modulating capacity. This is a 16,000 BTU capacity gas furnace. And you can see a rendering on the right of the approximate duct layout. The measured data was then used for comparison to the simulations, and so we measured things such as the exterior conditions and also the temperature within each room and the temperature at the discharge of each duct, as well as a number of specific components on the actual air handler, again, to really fully understand the performance so that we could compare it to these simulations. Another little interesting tidbit of data to point out is that static pressure was a primary concern using these smaller diameter ducts. And with the system that was installed in the lab house, again with these 12 2-inch ducts, we were able to deliver 260 CFM with only 0.32 inches of static at the plenum. So that's the amount of static that was available to the duct system. This system had a very minimal return, and so that certainly helps in being able to minimize the total external static pressure so that the majority of that pressure is available to the duct system. But again, we saw a lot of promising results here, both from a comfort performance and from an air delivery performance.
Okay, so moving on from our testing kind of phase of the project and looking at design methodology, we began conducting a series of simulations. And just to give you some basic parameters up front here, we were simulating a 2.5-inch ductwork, which we felt was going to be a more appropriate or suitable duct diameter for your typical production home. We simulated a single house geometry, the one that actually matched what we had installed in the lab home. And we did 3 climate zones, and we simulated a 2012 IECC enclosure. So a fairly ambitious enclosure, but not unrealistic, particularly given where codes are going in large markets. So the purposes, just to reiterate, for this simulation are primarily to study the impacts of temperature distribution throughout the home. And we wanted to compare those impacts between 2 systems, our plug-and-play duct concept and a more traditional trunk and branch duct system. Additionally, we used the simulations to compare the results from different design methodologies. So basically, methodologies that resulted in plus or minus a couple ducts per room. And it did influence the decision that Andrew mentioned earlier for design methodology 3, because it did indeed seem to have the best performance of the others. We needed our simulations to really accomplish a variety of things based on what we were trying to learn from this study. So we needed the simulations to be multi-zone, meaning that we would be able to predict temperatures in each room of the house, because we were primarily looking at the temperature difference between rooms, temperature uniformity. We also wanted to be able to simulate the duct system itself and the parameters of the duct system that influence the distribution of the air, such as the length, the fittings, and the roughness. We wanted to be able to include the interior state of the home, particularly doors, because we knew that whether the doors were open or closed were going to dramatically influence the mixing of the air between zones. We saw that a lot in earlier research with the Building America and our single point distribution work. And we also included some very basic models of air infiltration and also some internal gains as well to make it kind of behave realistically, and to be able to create a simulation that was accurately simulating the way it would behave as we saw in the lab home itself. So a quick snapshot of what the model output looked like. We were simulating thermostatically controlled, so you can see the cycling of the system. Summer, we did the plug and play, and as in this plot is labeled the flex system, and we have all the zones notated as well. So it's a pretty detailed and complex simulation. It goes beyond what your typical sort of rating model might do. We were using this to really compare fairly detailed phenomena. So we looked at a variety of parameters. One of the main ones was duct layouts. And on the left, there's the home run concept, the plug-and-play concept, and on the right, the trunk and branch layout as we modeled them in the simulations. The plug-and-play concept is envisioned as being more compact, and you can see that on the left. It's really radiating from the central point, and the kind of dispersion of the trunk and branch was far more spacious, you could say. But we were really studying the difference between these two layouts and their impact on temperature uniformity. We also used an airflow network implementation which simulated large openings such as doors and connections between zones, and we also simulated air infiltration to make sure we accounted for that sort of thing through the enclosure. Just a side note, we implemented the airflow network within Energy Plus, which was a challenge for our team because it was a new feature that we had never used before. The screenshot represents the kind of complexity of the components that you have to create within the model. There wasn't a large user base of this software to get a lot of debugging knowledge or tutorials per se to be able to implement this. So just to note, it was a real challenge for us. We'll offer out any advice that anybody else is trying to implement these things. We're happy to divulge any help that we may have learned. And our report goes into a little more detail about how this model was hooked up. We wanted to make sure that it was doing an okay job simulating the real world. So we created a simulation, or set of simulations actually, that closely matched what was installed in the lab home. And we took the monitored data and performed our delta T metric, which is measuring the maximum temperature difference between rooms, and we overlaid the model results. And so this is kind of our best model setup that we got. And we felt the agreement was pretty good. We saw the effects of solar gains creating that spike in temperature uniformity. And the error was really pretty good. The coefficient of variance you can see there is 15%. You may note on the second day we had a bit of a diversion, and we really feel that's explained by some of the components of weather and climate that we did not measure, as well as minor things. We feel the model did a pretty good job. And definitely we were exceeded our expectations. So as we moved through the analysis using the simulations, we generated this sort of plot to be able to compare models and compare the temperature uniformity result. It's a simple distribution, and it's showing two models. The distribution is the room-to-room temperature difference. So basically, further to the left is good. That means you have a more uniformly conditioned home. And the two models, red and green, are presented as the distribution. Their average delta T is that vertical line. And we have some basic statistics in the upper right-hand corner of the facet. We took note of the percentage of time that the temperature difference was within ACA thresholds. And we showed the average room temperature and the standard deviation. So I'll quickly go through some of the parameters to show their effects. We looked at duct leakage. We simulated leakage at the takeoff from the plenum of the traditional system, just to show to look at its impact on the uniformity. You can see it does have a fairly significant impact on the results between the red and the green models. In some cases it helped, in some cases it hurt. It sort of depended on the starting condition of the tight duct system. We also looked at interior doors. It's another factor that had a major impact on the distribution of the temperatures. And again, it's kind of a not necessarily always good or always bad, but it did have an impact dependent upon whether they're open or closed. And then another one, again, was duct roughness. We thought that we didn't look into detail about installation errors. We didn't simulate the roughness as, say, a runout that was heavily crunched and therefore didn't get enough air. We sort of just blanket applied a higher roughness to all of the ducts. and thinking that the higher pressure was going to lead to more uniform temperature, airflow distribution. And you can see the results just in this plot. So the main result of these simulations was to compare the traditional system to the plug-and-play concept and take into account all of these factors such as roughness and layout and looking at them in comparison. We wanted to see that through these simulations that the plug-and-play system was reasonably performing in comparison to something that's out on the market. And so the first plot here is of the summer. And generally speaking, we felt that the plug-and-play did a good job. Now, you could argue it's not good, but we felt like it's as good as your traditional system. And in the summer, we should note the airways are sort of the controlling sizes, or the loads of the rooms are controlled by the cooling load in the home. And so you can see that the results of temperature uniformity were pretty good in this plot. In comparing the green plug-and-play system to the red trunk and branch, in each of these three cases, all three climate zones, the plug-and-play does actually better than the trunk and branch. Now looking at the winter, we did not include any balancing difference between the two seasons. The simulations included the same airway sizing for each season, and because cooling dominated, the winter season saw much worse comfort. However, when comparing the plug-and-play to the flex system under the same level playing field of no balancing dampers, the plug-and-play also exceeded the performance of the traditional system. So in a nutshell, we felt through this simulation exercise we were able to study over a wide variety of climate zones and configurations that the plug-and-play consistently was as good or better than the traditional system. So we were quite encouraged by these results.
Yeah, and just for reference, we ran these models as a really comparison between the plug-and-play and trunk and branch. We did those in 3 different climate zones and just used that one house type. We used the architecture of the lab house and put it in different climate zones with different levels of insulation, different code levels to really understand that relative performance. And again, we go into all of that detail in the report, but this just provides you a quick snapshot to kind of show you that yes, there's a lot of promise here with this proposed technology. So next we'll go into the cost analysis that we did. This is primarily a time and motion study where we're comparing the plug-and-play to the trunk and branch system. At the end of the day, the primary thing that is going to get this technology adopted is whether or not it actually is cheaper to install, if it's quicker to install, and if the materials are also inexpensive. And so, we saw a lot of promise based on the performance of the technology. The design methodology also provides a streamlined alternative that again can deliver comfort in a home. But ultimately, what it boils down to is, can it be installed quicker? That's really the goal. And so we'll explore that now. We did this time and motion study in a 2-story townhouse mock-up that we have, and the ductwork for all 3 of the cases we looked at was installed within conditioned space. And the same tradesman installed each duct system, and we basically used time-lapse photography to time the various installation durations for each of the systems. The 3 systems that we looked at were a conventional trunk and branch system, a 2-inch PVC plug-and-play system, and a 2.5-inch PVC plug-and-play system. That trunk and branch system used kind of a steel trunk with flex duct runout. And here you can see a drawing of each of the system layouts. On the left, the trunk and branch system, that utilized primarily ceiling and floor registers. So the second floor had floor registers, the bottom floor had ceiling registers. And this is very typical of practice in the field today. Because this main trunk was installed within conditioned space, it had to go in a bulkhead, which was located on the far left side of that main living space. The 2-inch plug-and-play system then was installed primarily, or entirely rather, within the floor cavity, and it had a combination of high sidewall registers on the second floor and high wall and ceiling diffusers on the first floor. And then something to point out also was that the 2.5-inch ductwork that we found through the exercises of this project, the 2.5-inch PVC simply wasn't flexible enough to easily install it within the floor cavity. It would have needed to be able to be bent much more to get it in there, and so we actually had to install that ductwork in the bulkhead as well. And we'll see how the numbers played out. But despite that, the 2.5-inch ductwork still had much less installation time than the traditional trunk and branch system. So here you can see a couple photos of the installation effort. Again, you can see that ductwork installed within the floor cavity and the trunk and branch system as well. And again, you can kind of see that the 2.5-inch PVC also had to go into that bulkhead. So the results, what did we see? Ultimately, we did see a big labor savings in doing the plug-and-play system. So you can see that the traditional system took a total of 18 hours to install, and I will point out that this was two people working simultaneously, so that's 18 quote man hours to do the work. The 2.5-inch PVC system then took 10 hours total time, and that includes the 6-hour bulkhead installation. And then the 2-inch PVC took a total of 6 hours, and that system did not need the bulkhead. And so if you do the math briefly, the 2.5-inch system, just the ducts took a total of 4 hours to install. And if you compare that then to the 6 hours of doing the 2-inch PVC, the reason for that was that based on the design methodology, the 2.5-inch system needed a couple fewer ducts, and so it was able to be installed a little bit quicker. We had a basic labor cost assumption. The material costs showed some interesting outcomes where the 2.5-inch PVC was significantly more expensive, and a large part of the reason for that is that it's a diameter that's not readily available. It's more of a specialty size, and so the cost is much higher. And also, Schedule 40 pipe was used kind of as a readily available surrogate material. We envisioned that this duct system could use a much thinner walled material, and that could ultimately bring down the cost further. And so then when you look at the total numbers, partly because of that elevated material cost, the 2.5-inch system and the traditional system had similar total costs. The 2-inch PVC, however, shows significant cost savings. And again, this is a very early kind of estimate. We believe that there's possibilities for further cost reductions through kind of streamlining the process and for developing kind of a commodity duct, plastic duct material. So now the last portion of the work that we'll talk about is efforts in engaging the codes organizations as well as the home building industry, and then we'll go into some of the final conclusions. So we held an expert meeting with code officials primarily to discuss the issues with fire code and acceptance of the plastic duct material. So like we mentioned before, PVC pipe doesn't meet the residential standards for air delivery ductwork, and we really wanted to understand why that was, to understand if there's ways around that concern or that issue. And so we held this expert meeting with code officials, and the primary concern that came out of that was the fact that air ducts connect many zones, many spaces within a house, and they provide a conduit for combustion spread. So we all know that obviously PVC is used in construction. Why couldn't it be used for ductwork? And also plastics are used in various components of air delivery systems. It can be used in registers. An air handling unit often has plastic ductwork. But again, what it really came back to is the fact that an isolated piece of plastic is okay, but when it spreads throughout the entire house, there's a concern there that fire could spread through that conduit. Flexible ducts that are on the market today are also often plastic, and the reason that that's accepted is because it would burn so readily as to not really spread the combustion. And so that was kind of the total outcome of that work. Ultimately, either you need to have a plastic that does not allow for flame and smoke spread, or you would have to have some mechanism, a fire stop mechanism between spaces to prevent any spread. Discussions with the building industry showed a lot of excitement and interest in this technology to see where it pans out. There's a strong interest in understanding ways to reduce labor and time and effort in installing a good HVAC system. And so there's a lot of interest to see the potential for this high-performance HVAC system that's able to be installed much more quickly with less potential for a poor installation. So kind of the final outcome is that we looked at some of these other materials that were code accepted that could then be used in a house tomorrow to do this kind of a system. So just to recap on then some of the advantages of this system, the home run plug and play system, it's easier to install within conditioned space because of those smaller duct runouts. It's quicker and cheaper to design and install. And in terms of the installation quality, we believe that there's a much less risk of an installer, basically doing a poor installation and having comfort issues down the road. Another big advantage is the fact that it has fewer unique parts. So instead of having, maybe 30 or more unique fittings and ducts and components for a conventional system, you might get by with just a few unique fittings and components. So that can help ease some of the pain points in the industry. Like I said, there's less chance of an improper installation, and by its nature, it has lower leakage. The simulation effort that we conducted and some of the lab house monitoring showed that this system can provide similar performance, if not better, to conventional trunk and branch systems. So it provides that level of comfort that's expected. The small ducts better match low-load homes and the amount of airflow that they need. In doing some of our early design work, we kind of realized that there's almost a need for HVAC installers to be using 4-inch ducts and 4- and 5-inch ducts more frequently, I think, than they are used to maintain velocities that are expected. Again, this is because airflows have come down as loads have come down, but often in the industry they're still using the same duct sizes. You get better throw mixing from smaller ducts, and this is something that's been explored in past research, but it's still very relevant. And then another concern that people have often raised is whether or not noise is an issue. And what we've found is that using kind of an open outlet, you really reduce any potential for noise propagation, as opposed to a diffuser type grill, which might generate some whistling or noise right at the terminal. So some of the challenges then that still exist would be, there's a greater need to integrate the duct layout with the framing of the house. That's really to ensure that compact duct layout. Reducing the length of the duct really plays a big part in making this a viable technology. And then also, codes are still something of an issue with the original rigid duct material. However, we did explore those alternatives that still have a lot of the same performance characteristics, but are code accepted. So at the end of the day, we think that there really is a lot of promise with this technology. It still needs some of the polish and fine-tuning before it's maybe market ready. But I think that this is something that can really is poised to revolutionize the industry. So some of the next steps, we're looking to basically commercialize this technology and work with manufacturers to take it to the next level. We would want to demonstrate performance in occupied homes, and that would really provide kind of a final body of evidence to show that this is a really viable technology. And then also considering the possibility of continued code acceptance of commodity types of plastic duct materials. So just some final conclusions here to leave you with. We looked at, again, these couple of main categories for understanding this technology. We looked at the performance, both from a comfort and from a air delivery performance. We looked at the cost, primarily the labor cost. And then we also looked at the design methodology and market interest and engagement. The performance of that 2.5-inch to 3-inch ductwork really showed that it could provide comfort in a wide variety of homes constructed in the U.S. We think that's kind of a sweet spot there. And the simulations showed that there was similar, if not better, comfort provided by the plug-and-play system relative to a trunk and branch system. The time and motion cost study showed that the plug-and-play system actually has a lot of potential for cost savings and for time savings on the installation. And then the design methodology panned out to provide this more streamlined solution for designing the duct system. And then ultimately there's I think a lot of excitement and interest in the market for this technology and for innovation in air delivery in general. So here's our contact information. If you have further questions, again, that final report will eventually be published by the DOE. It's currently undergoing some of the peer review phases, and that goes into much more detail at all of the aspects that we considered. But again, thank you for your time and interest in this project. And I think at this point it will be opened up for questions.
Great. Thank you so much, Andrew and Rob. And just as a reminder, if you haven't had a chance to submit your questions, feel free to do so in the next few minutes. Andrew, Rob, we did start getting questions about within a few minutes after you started presenting. So feel free to, in responding, if you need to go back and reference a specific slide or anything like that, feel free to do that at any time. The first question, and we're just going to start at the beginning, so this is going to be definitely at the beginning of your presentation. The first question that we have is, has this been used with both vented and unvented attics?
Yeah, so the work that we've done so far has primarily considered this as being installed within conditioned space, and so we haven't yet studied the way that this might work in an attic. So I guess the answer is kind of neither. We think that with certain construction types, this would certainly end up in an attic. And I think that as long as the ductwork is buried and encapsulated in the right way, there'd be potential to use this in an unvented attic. Certainly condensation would be a concern, I think, with PVC, and perhaps that's where the question is getting at. But as long as that's properly encapsulated, I think there'd be a way to do a good design to get that to work.
Okay, great. And speaking of PVC, the next question is that it says, This project sounds interesting, but isn't PVC a red-listed product?
Yeah, so I guess I don't know entirely what red listed means, if that's an environmental concern or fire concern. Maybe the rest of the presentation got into some of the fire concerns there that, PVC, yes, we recognize isn't a material that could be used right now for ductwork. But we really felt it was a good example of what this material might look like, that there are other plastics that could be code accepted that have better flammability properties. And then there's also other materials such as that 3-inch flexible ductwork that's code accepted that again could be installed readily.
Okay, in addition, another PVC related question. Have you considered VOCs in the air supply from PVC ducts in your testing and health effects from long-term exposure by occupants?
Yeah, so that's not something we've considered specifically yet. I agree that would be a concern. We don't want to go and install a material in an air delivery system that somebody might be breathing in over their lifetime or even 10 years that could have negative health concerns. We were primarily looking at the basic air delivery performance, comfort performance, but I think that would be definitely something to consider in terms of commercializing a product.
Okay, the next question is about the lab house. Could you elaborate on the makeup of the lab house, specifically in terms of insulation?
Yeah, so the lab house, and I'll flip forward here if I can get to that slide. You can see a photo of the lab house on the top right here. And this house had R40 walls and an R60 attic insulation. And it had triple glazed windows. Various duct blaster tests, or not duct blaster, but blower door tests have shown that the air infiltration is well less than 1 ACH50. So the lab house is a very, very low load home, very close to what a passive house might be. And we certainly recognize that, yeah, 2-inch PVC or 2-inch plastic duct might be sufficient for this very low load home. But whenever you can increase the duct size and still provide enough energy for a less insulated house that might be more typical of what's being built by a production builder today. So I hope that answers the question.
Great. In this one, if you have comments, the statements about home run water distribution, it can be a disaster for heat loss and water waste, as well as large increase of material use. Do you have any thoughts about that?
Yeah, so that's kind of the last point there has also been something that we've been somewhat concerned about, is the fact that, having more runs could increase the total amount of material within the ductwork, as opposed to that trunk and branch where that might be a more material minimal scenario. That would again be something to, if that's really a primary concern, that would be something to explore further, kind of the total material impact that this might have. We think that some of the commodity materials show the potential for cost savings, and so we've primarily been focused on cost savings here while delivering performance, but there might be other ways to optimize this where total material usage is at a minimum. To kind of get at the point maybe with water usage, ductwork and air delivery sees a very different flow pattern and use pattern relative to individual faucets and fixtures. So I don't think that would be as much of a concern when we're using this same home run thought process. When we're using it for air delivery, I don't think there's some of the same concerns relative to plumbing.
Okay, and with this next one, let me know if it's a long one, so I'll try to provide a summary. but zoning efficiency is the issue. In a 4,000 square foot Texas high-performing house, is it better to use one 3-ton unit in one zone or two 2-ton units in two zones?
Yeah, so from a comfort perspective, certainly using more units and more zones is going to perform better. And that's something that, is somewhat, a separate issue to the specific technology that we're looking at right now. In terms of using one unit versus two units, that's something we've considered with this technology, and we think that there might be some upper limit on the total square footage that's feasible to condition with just one unit. This technology is a bit more sensitive to total duct length compared to some of the larger diameter trunk and branch systems, where you might a little bit more easily get away with one big system. This home run plug and play technology would be perhaps better used if it was broken into two systems that could bring down the total lengths of the duct runout. But again, with this particular effort, we were really focused on kind of that middle size of production homes, somewhere maybe between 2,000 and just somewhere just over 3,000 square feet, where we think is kind of the sweet spot. So hopefully that answers that question.
Thank you. So the next one is, if you install a 2.5 to 3-inch duct in 2x4 interior walls, how will this affect structural integrity of those wall studs?
Yeah, so with the way that we believe the routing would work, you wouldn't necessarily route the ducts through a 2x4 structural wall, that it would go vertically, up through a wall. And so the ways that we've been able to install the ductwork so far haven't had any issues with structural deficiency. I can certainly understand, if you try to route a 3-inch duct horizontally through a stud wall, you're going to eliminate a lot of that structural member, and that wouldn't be a good scenario. And so that's why we're really looking at vertical runs through those stud walls, and then the horizontal runs through other types of stud bays in the floor cavity, kind of above or below a zone.
A quick question about another one about the lab house. Was it occupied?
So it was an unoccupied house, and at this particular usage of the lab house, we did not have any simulated occupancy. Now that could certainly change some of the relative outcomes, or not the relative outcome, but the absolute outcome of this work. But part of the reason we didn't simulate occupancy was to make it a little bit easier to compare the measured data to simulations.
Well, when we were comparing the measured simulations, we didn't have occupancy in there because the lab home was not occupied. When we were doing the ultimate comparison, we did include internal gains that accounted for people. One of those. Yeah, and just as another interesting thought related to occupancy, in the past we've done work in the lab house where we have simulated occupancy, and it's interesting in the winter, during mild winter days, we found that simulated occupancy was nearly enough to condition the spaces without the systems even kicking on and running. And so that was another reason, was to really be able to see the impact of the system operation and cycling on comfort. But that would, in many ways, be a next step, is to install this in an occupied house and to see some of the performance in that scenario.
Great, thank you. The next question relates to the charts, I believe, that Rob was showing. Why is DT higher in winter than in summer?
Okay. These two probably? Okay, correct. So that's primarily due to how we ran the design methodology. So the design called the dominating load was the cooling load in most of the rooms. So that means the number of ducts put in the rooms were typically controlled by the cooling load. And when we ran the simulations, we didn't adjust the number of ducts for the winter months. So that means that many of the rooms were receiving too much air in the winter. So some of those rooms that had a very high cooling load, say the south-facing and west-facing bedrooms, they were getting way too much air in the winter. And so therefore, when we run the simulation in the winter with the kind of single balancing ductwork, that you see these higher delta T's.
Yeah, and so that's something that's kind of a bigger issue / concern within HVAC, is that often systems are designed and installed with one balance, and that means in one season or another, there could be potential for comfort issues, depending on which season has the predominant load. And just to point out something else here on this image, on the cell to the right, so climate zone 5, we see that there's a 15.5 degree and a 9.6 degree room-to-room temperature difference, which might seem extremely high. However, those types of numbers have been seen in the field before. We've seen up to 10 degrees, say, Fahrenheit on a room-to-room temperature between floors on 3-story townhouses. And again, a lot of that's driven by stratification and differences in heating and cooling load and needs. On a large townhouse, you might need to deliver the majority of the heat to the bottom floor in the winter, and then conversely, you might need to deliver almost all of the cooling airflow to the top floor in the summer. So there's really a bigger challenge in conditioning some of these types of houses, especially with these big changes between heating and cooling loads. So that was kind of what was driving what's observed here.
I think we would also note it's an advantage of the plug-and-play system with the central location of the manifold, that every duct is going to be accessible, and the installation of balancing dampers is conceivably going to be a tad easier because there's an obvious place to put them.
Okay, great. Thank you both. The next question that we have is, did you perform a manual T analysis? Do you get better throw with the PVC system?
Yeah, so some of the past work that we've done has looked at that question, and I don't have any of the slides here, but we've given presentations in the past that have images showing the throw specifically from well, yeah, we actually do have some slides showing that out of the smaller diameter systems, and so the image here on the left, which we conveniently have in the presentation, shows some CFD work that was done to look at throw and mixing and stratification with different air delivery scenarios. And the small diameter systems certainly have much better throw performance relative to a standard diffuser, especially when we're talking about some of the lower loads and lower airflows with modern efficient homes. There's certainly a bit of a concern if you have this higher velocity of air coming out of a small outlet, that air might impinge upon an occupant somewhere, but that's where good design and these high sidewall types of outlets come into play, that air is typically mixed across the top of the room, then mixing down and providing even comfort throughout the space, and not blasting some occupant somewhere with this jet of air. But yeah, that's something we've looked at in the past, and these small diameter outlets can actually, when done correctly, provide really good mixing and throw.
Okay, thank you. The next question is, if most HVAC contractors don't have a clue on standard systems, what is the reality in cost and performance I'm sorry, hold on. So if most HVAC contractors don't have a clue on standard systems, what is the reality and cost and performance would be to learn a new system well?
Yeah, so that is a very good concern. You know, we throw something completely different at these contractors. You know, if they're not even doing today what's expected of them particularly well, can they be expected to pick up this whole new system and to do an even better job with that? You know, there certainly would need to be some training associated with this new system, and ultimately, though, we feel it comes down to the fact that there's fewer parts. It's a much more streamlined system, and so we think that while there might be a little bit of a learning curve initially, that trade contractors would very quickly pick up on the idea, and that ultimately then the installation quality and time would be much more favorable with the plug-and-play system, largely just because it's much more simple to kind of rationalize the design and installation. You know, especially if we're only talking about one duct. You know, you can't put in by accident a 7-inch duct where you meant to put in a 12-inch duct or something. It's one size, and so it eases some of those potential mess-ups that can occur in the field.
Another thing that we've talked about and through some of the learning that's occurred through this project is that we feel like the plug-and-play is going to be more resilient to error due to its design methodology. The kit of parts is far simplified, and if you're talking about a single diameter, there's much less room for error in sort of sizing the airways and some of the things that are difficult when, say, you're on the cusp of a 7-inch versus a 6-inch. Those changes in diameter can really impact the performance of the system. And additionally, I think the simulations showed they're also less sensitive to, the plug-and-play system is less sensitive and less, it needs, it's less of a need for balancing dampers if the number of airways is roughly correct. We're looking in the future to sort of dig into that question a little bit more and really kind of explore the design methodology, but we do feel it's a more resilient system due to its simplicity and componentry and also the higher resistance and some other factors that lead to more predictable airflows.
Okay, great, thank you. The next question is, what was condensation and potential mold growth looked at?
So that's definitely a concern that we're aware of. That's been raised, you know, various times, and I think it really is a legitimate concern. That wasn't something we looked at specifically. With the ductwork being installed within conditioned space, there is less of a risk of condensation and mold growth. You know, if there was some scenario perhaps where air sealing wasn't done well and you had extra humid air maybe in a floor cavity, there could be some concern there. And so that would be part of the you know, ultimate, say, design of this duct material is to understand, you know, what are the limits of surface temperature, and you know, that may necessitate, say, a small amount of insulation contained within the diameter of the ductwork to basically ease some of those condensation concerns. So certainly something we're aware of, wasn't specifically targeted here, but something we're thinking about moving forward.
Thank you. What about static pressure requirements and resulting fan power requirements for the two concepts?
Yeah, so fan power and static pressure is definitely kind of the biggest thing that we've been trying to understand with this effort, along with the comfort performance. The measurements that we have from the lab house were a bit better than we expected. You know, we thought that maybe we'd be pushing 1 inch of water whenever we were putting those 260 CFM through the system. And let me just flip back to that slide there. we're able to deliver 260 CFM with just 0.32 inches available to the duct system. That might be a little bit high compared to targets today, but from our experience, field installed duct systems have much higher external static pressure than they're designed for. That's for a number of reasons, and we think that this system has the ability to be much more predictable in that total static amount. So an ideal trunk and branch system, when installed perfectly, could have less static pressure and less fan power than the plug-and-play system. But I think when we really look at the real-world scenarios, the plug-and-play system has the ability to be much more reproducible. And so we can kind of dial in that static pressure and, by varying the size of that duct, kind of dial in that sweet spot. And that's where, we've found that somewhere around 3 inches provides a good balance of airflow and static pressure. Whenever we did the range of applicability testing here, whenever we were looking at the 3-inch flexible ducts, we considered 16 of those ducts at 30 feet average length, and we assumed that we would have 0.35 inches of water, which isn't, extraordinarily high. We're not talking about a 1 inch or 1.5 inch of external static pressure, but just looking at 0.35 inches, we're estimating that you would get over 1,000 CFM through that 3-inch duct system. So that would be enough for a 3-ton air handler without imposing an extremely excessive amount of static pressure and fan energy. So a lot of it comes down to making a much more compact duct layout, that the total lengths are shorter. So even though it's a smaller diameter, you have shorter lengths, and that helps to reduce the static pressure. And then also one of the benefits of the plastic materials are their smoothness. And by not having those rough ridges from a flex duct, you can further reduce the static pressure requirements while maintaining the airflow. So certainly a big concern, and we recognize that for this technology to be widely adopted, there can't be a big increase in static pressure or fan energy. And so that's something that we're trying to minimize through the design of this technology.
Okay, and we'll go through a couple more questions. We don't have time to go through all of them, unfortunately. But the next question, any issues integrating with DWV or water distribution or other infrastructure?
Yeah, so that would be something in certain areas that could be a concern. If you're trying to pack 5 runs down a corridor or something to one end of a house, and you also need to run a drain pipe or other plumbing, that could be a concern. With the smaller duct diameters, you still have enough space around that ductwork, I think, to be able to fit some of those mechanicals. But that would be part of that kind of initial installation, market exploration process, is to better understand some of those types of concerns so that they can be avoided. But yeah, definitely another very good point, and something that we're thinking about.
Great, thank you. Do you have a solution for the fire safety issue with existing materials?
Yes, so the material that we've been looking at now, which does meet all of the flame requirements, is a 3-inch flexible duct material. This is similar to conventional flex duct. It's a bit more robust, a little bit stiffer, and that is accepted by the codes. And so that's something that we've been that we had explored through this project, and we think is the most promising kind of immediate way to bring this idea into the production world. So yes, that's exactly what we're looking at right now.
Okay, the next question is about ductless systems. Have you looked at how they can marry with this plug-and-play concept?
Yeah, so that's not something we've looked at specifically. I think that...
Well, we should say the first testing we did in a prior project of a similar small diameter system was hooked up to a ductless unit.
Ducted mini-split.
Ducted mini-split.
Yeah, unit. There could be great scenarios where you could have a hybrid approach where maybe the plug-and-play system satisfies the majority of the smaller rooms within a house, and then if you had perhaps a big bonus room or a big game room, maybe that room would have a ductless mini-split. So there could certainly be scenarios where that works really well, but that wasn't something that we've looked at yet specifically. But again, a very interesting thing to consider.
Great, thank you. And just one last set of questions before we go into a couple of polls, which will only take our participants just a few minutes. But Andrew, Rob, can you speak to, can you elaborate on your return strategies, and can you provide specs on your AHU?
Yeah, so the AHU was again that modulating furnace, and in the report it kind of breaks down in greater detail the specs there. But that was a 1.5-ton coil and a 16,000 nominal BTU modulating furnace, and that the airflow that furnace was delivering was somewhere typically between on the low end it was 140 CFM, and on the high end just about 160 CFM. So that was 260 CFM. So that was the specs on the air handler. And then in terms of the return strategy, again in this little rendering here, you can see that the air handler, which is that larger box, is sitting on kind of a squat box, and so that was our basic return plenum. It was as short as possible, a single return, and one of the other things that we found is that when we're talking about these lower airflows, door undercuts were sufficient actually as a return air strategy from the rooms. So we measured the airflow out of a duct or several ducts in a single room with the door open and closed. That airflow did not change, and also whenever we closed the door, there was no measurable static pressure buildup within one of the rooms. So that's one kind of advantage of this proposed technology, is that it can streamline the return air strategy significantly. So there'd still be some thinking, I think, in design to make sure that that's going to work in all cases. But with what we're looking at here specifically, we were able to get away with that.
Great, thank you so much. And we know that that was a lot to speak for so long, but for our participants, we just have a few poll questions to get some feedback on the value of our Building America webinar today. So here in another second, you should be able to see the very first poll question. And if you could just respond on your screen, we'll give you a few seconds, but we would love to get your feedback on the content of today's webinar. Okay, great. The next poll question that we have are about our presenters today. If you could just spend a couple seconds and respond in terms of and provide feedback on our speakers, we'd appreciate it. And our last poll question today is just to get some very general feedback. So we appreciate your time today, and as you are responding to this, we are going to be wrapping up today's webinar and providing the address where we will be posting the presentation slides as well as the audio recording. So with that, thank you again to Andrew and to Rob today from IBACOS for sharing information on their project. We want to make sure that you can see the website address on the screen. That is where you can go to get copies of the presentation and the audio recording today. It'll take a few weeks for the audio recording, but you can always return to that website. Also, in addition to the past webinars as well as today's webinar, the Building America website, you can subscribe to the latest news and updates in regards to webinars, recent reports, and those types of resources. With that, we just hope that you have a great day, and we do appreciate your time today. So have a wonderful week, everyone. Thank you.